Thank you. Thank you for coming. Okay, so a little bit about me, and then we dive deep into this because I assume none of you know me. I'm the co-founder and CEO of Bauplan. I'm a serial entrepreneur. I built a natural language processing company before this called Tuso, brought it to acquisition, and then led AI and ML at Coveo from scale up to IPO. Essentially, my team and I build recommender systems, search, AI search, and a lot of analytics systems for hundreds of enterprise customers and the data infrastructure to support it. So these days I'm working on Bauplan, which is basically a serverless lakehouse that is really focused on the Python experience. And we'll see that in a second. So today we would like to talk about what we did with one of our early adopters and how these folks migrated from a more traditional data stack based on a number of AWS technologies, but based mostly on Hive, onto a simpler design heavily based on Iceberg. The result of that is essentially a simpler, more affordable, and just like easier infrastructure for them to work on. We're going to talk about the lessons learned in doing the migration. We're going to talk a little bit about what use cases we enabled, because a lot of what we did was around enabling a wide range of use cases, including AI, data science, and ML. And then we're going to just like talk about like why Python is very useful and very important in the lakehouse experience. So that's it. So let's start right away. So Mediaset Business Digital is part of Media for Europe. This is the second largest broadcaster in Europe. So we're talking about a company that is listed in several countries. They have, I think like around like $4 billion in revenue, more than 70 million users, presence in several countries and dozens of different media touch points. The business digital unit is more about like those touch points that are specifically digital, and it's a little bit of a galaxy of web TVs and channels, pay-per-view, web radios. So there's a variety of touch points there, and they process like a remarkable amount of data. They have like more than 25 million registered users, billions and billions of views for their programs. And almost 80 petabytes of data processed. So the data, the size of the data somehow raises some challenges in the infrastructure and how to handle that. What really the company is about here is enabling a wide range of use cases, because the company has, like when we first got in touch with them, you can see that there are like more internal use cases, like there's a lot of ad hoc data science happening. Business intelligence, of course, like BI, and it's like mostly kind of like SQL and warehouse world there. But then it kind of like progressively goes on to more complex things like analytics, product analytics, real-time analytics. Now you have machine learning, but this machine learning are actually applications. So you have like recommender systems, ranking functions for search, conversational agents, and sometimes even, this is one of the use cases that I'm going to show, super gnarly data science stuff that they need to optimize their advertisement business, which is kind of like a very articulated and complex data science use case. So there's a bunch of stuff they need to do, like from notebooks to actual applications that run in production every day at a massive scale. So they really wanted to have like, to build like a data platform that is very flexible, because they needed to do like essentially the entire range of possible applications you can have on data. At the same time, this is a large company, so it's a complex organization. You have a bunch of people, you have different teams. I'm gonna say like not all of them are actually like super familiar with big data technologies, so like not all of them spent the last 15 years like learning Spark and Hive tables. But they do have a lot of developers, so there's tremendous value for them in unlocking these developers and just like lowering the entry bar so that we can have just like regular folks that understand the business very well, and they can actually work with the data without having to go through the data platform team all the time, which, as good as the data platform is, given the size of the company, kind of naturally becomes a bottleneck, and even if nobody likes the situation, right? So really what we're talking about here is that they wanted a simple data platform that enables the largest number possible of developers, okay, to do a lot of stuff: analytics, data science, and AI, okay? So this is what they had before. This is like their existing stack. And throughout my career, I think I saw variation over the theme of this data stack several times. So it's pretty, fairly traditional. So they went for a data lake, of course, because they're a large company and they needed that flexibility, so everything is on S3. There's a lot of AWS, there's a lot of Hive tables in AWS Glue, and then there's really a lot of Spark, like a lot. So there's essentially Spark is used there for a variety of use cases. Batch use cases at large are mostly done with Spark. So it goes from feature preparation, data transformation, or just like good old ETL. And it's also the go-to language for the data science team to do like more machine learning and AI kind of use cases. And then, like for interactive use cases where you just like query and you have analytical use cases, things happen mostly in Amazon Athena and Redshift. And that is kind of like more BI usually. So this is like the general architecture. So what are the problems? Now, okay, so this is an Iceberg conference, so I could probably complain about Hive table for like 5 hours and everybody's gonna be just like, yeah, okay. But I would like to make like a more, like a kind of like a broader point about this and how, what is the role of Iceberg in the lakehouse design in a more kind of like business-oriented mentality where you want to simplify your stack for a very specific reason. So I'm going to focus on actually problems that are more architectural, like this. And I saw this like several times. There's two stacks. There's one for the analytics and there's one for ML and AI. It's always like that. And keep those two things in sync is a gigantic pain in the neck. And you usually have, okay, so your analytics stack is not that bad. You have your, like your data lake, and then you have to ETL your data into the warehouse. That is a bit of annoying. You have to make sure that these two things are synced. But once the data is in the warehouse, honestly, the developer experience of the analyst, of the person who writes SQL, it ain't that bad, right? Like it's okay. They can basically run SQL and run it in the cloud at scale, see the results in their BI tools. In this case, these guys are heavy adopters of Looker. The machine learning and data science stack is usually way, way more messy than this. So you have some data is in Hive tables, some data is just a bunch of files. I don't really have a way to do my versioning and do point in time, but I'm a data scientist, so actually half of my job is to iterating on different versions of data sets, and now all this problem is on me. Plus, when I am done, I probably just have a notebook that I attach to an EMR cluster. So what am I supposed to do with this thing? Well, you can schedule the entire notebook, but now you have a problem because you have a monolith that nobody can really debug, and it's kind of hard to keep track on, that runs in a dark corner. Or I can refactor that, right? And I have, okay, now I have several EMR jobs that work like a pipeline. But now every time I have a containerization, start the EMR cluster, do my thing in the EMR cluster, go back to S3, do it again and again and again for the length of the pipeline, which works in production, is definitely more testable and easier to debug than just one gigantic notebook. But if you have to change one line of code in this thing, it takes a day, right? So this is kind of like one of the main problems that you have when you have to do like data science on a data lake. Plus, really simply put, there's kind of too much Spark, guys. Like there's, it's just very hard, and a lot of developers don't really want to deal with that. Like this is, like the JVM error that Spark throws at you when you lower your guard. So for them, this was actually a friction to adoption. So we have like a lot of data scientists and people that are like really Python first, and the Spark, the massive use of Spark ended up being a problem for them to, democratize as much as possible to developers their data functions. So why Iceberg then, like in this context? Because then they started looking into, lakehouse designs and why using Iceberg. So there's 3 points that I want to make. So one is a very obvious point, but I cannot stress this enough. Iceberg is awesome because you don't really have to migrate. I mean, you have to migrate, but not really migrate. You don't have to move the data. The data stays in S3. And for anybody who ever migrated inside or outside of a data warehouse, you know that that is really, really appealing. So you can start your migration without having a massive commitment of a job that becomes like a year endeavor. Because of Iceberg, Iceberg also supports multilingual workloads. So you can do both SQL and Python. And for these guys at Mediaset was very, very important because they needed to do a lot of data science and machine learning. And the last point is Iceberg actually has a lot of very good abstractions for data science and AI. And I think this is a bit of an overlooked point right now in the community. And I don't exactly know why. It could even be that it's just, maybe it's just echo chambers. Like most people that I know that are really into machine learning don't really know a lot about Iceberg. And most of the people that I know that are really into Iceberg don't spend a lot of time doing machine learning. So maybe we just don't talk to each other enough. But what I'm trying to say here is that Iceberg is not a platform for you to do data science immediately out of the box, but a lot of the primitives, especially around point in time and time travel, are really, really good for AI and ML because 90% of your job is going to be, if you're a machine learning engineer, iterating on different versions of data set constantly, training a different model on a different version of it and keep track of all that. A lot of what the MLOps industry produced in the past 5 years is sometimes really look like reinventing Iceberg. And I think like this is a point that is important when you build like your lakehouse. Iceberg is actually good for data science if you know how to expose Iceberg to that crowd. So we decided to consolidate a new architecture on Iceberg. This is a large company, so initially they started with a POC with a couple of renegade engineers who were trying to do this, and then talk themselves into this is a good idea. To do that, they chose Bauplan as the platform with which they consume most of their data in their Iceberg lakehouse, and in the way they migrated from the previous stack to this new design. So I'm going to say something about Bauplan because I assume you guys absolutely know nothing about it. So Bauplan is a Pythonic lakehouse platform. It's essentially built natively on Iceberg and allows developers to run pure Python serverless functions against an Iceberg lakehouse to build their workloads. And the Iceberg lakehouse has Git-like semantics, which is, in this specific case, based on some abstractions from Nessie, if you are familiar with the project from the folks at Dremio. So how does it work like at a high level? This is what it looks like. Your developer is going to write Python functions in an IDE, okay? Those Python functions are just Python functions, okay? These Python functions have only one particular thing. They take a table as an input, they spit a table as an output. When they have to run those functions, they run those functions against a cloud runtime that we built that is going to take that function, containerize it, run it, so provision and configure the compute automatically to run that function, and write the output of that function as an Iceberg table back in your lakehouse, okay? When you want to do something that is more complicated, you just chain the functions together. That's all. We also provide a way for developers to inspect the data in an interactive way using DuckDB, also as an ephemeral function. That's kind of like an implementational detail. But really what the platform is about is, can I just write a bunch of Python functions and create a pipeline out of that and run them against S3 directly? The runtime is optimized to do this job, particularly in the lingua franca that speaks across the nodes is Arrow. So that's why like the runtime is particularly fast. It's remarkably faster than what you're used to if you run Python either on local machine or just like kind of like a generic runtime. A lot of the design effort went into designing the function Because one of the things that we really, really, really wanted is that the developers should be able to use this system without learning anything more than they already know. And so this is a typical function that you would write in this system. You have a couple of decorators there that are going to tell you whether the output of the function is going to go back into your S3 bucket as an iceberg table. And they're going to take care of your dependency management and containerization. So, you know, like for this function, I need pandas 2.2.0. I declare that in the code. The platforms take care of making that a container and running it for you. The same can be said for the input table. So in the blue in the blue square, you see what is the input table of this function. This is, as a matter of fact, an iceberg table on an S3 bucket. But as you can see, the developer doesn't really have to know that this is an iceberg table. All they need to know is that this is a table. So you have columns and you have filters. This is your input. That's how you declare it in the code. The system should find the right way to transform this into an S3 scan that is optimized to run this against your iceberg lakehouse. And then in the red square, that's just you being you. That's just Python code that you write. So the developer really doesn't need to know a lot about the platform or a specific framework or a domain-specific language. It's just Python functions. No need to know Kubernetes or Spark. No need to know about data lakes and data and tables. Really no need to know about containers as well, okay? I mentioned the Git semantics. So the other important feature of the platform that we built is, and is based on Nessie. So shout out for the folks at Dremio who supported us in building, in bringing those capabilities inside. How many of you are familiar with Nessie? Okay. So essentially, Nessie allows you to have multi-table abstractions when you do a branch. So instead of having just like one iceberg table and different versions of that, you can create a branch of like multiple tables. So it looks a little bit more like Git. We embed Nessie and then we expose that with our own APIs. But what it looks like to develop in the system is, I'm on my data lake, I have a bunch of iceberg tables, and I'm gonna create a branch like I would with Git. And now I have a sandbox 0 copy of those tables. So I can work with real data, but I don't have to worry about disrupting tables that are important for downstream consumers in the production environment. Then I run my compute with those Python functions. They are very simple to grok together. And when I am done, I'm gonna merge this table back, this branch back into my main table. And what I have is my new artifacts in my data lake. That's how it works. So this script is an actual script in how you would, for instance, import a new iceberg table in your data lake, in your lake house. So this is, kind of like the atomic function of what the migration is going to look like. You just do branch create, and you create an import branch. Then you do table create, name of the table, where the data that is going to be the table is, import the data, run whatever compute you want, like whatever job you have that involves that table, by just telling me where the code of the pipeline is, and then merge it. There's the Iceberg APIs are completely abstracted away, so it is the runtime. So it feels just like a Git flow. This is great if you're looking at the terminal, which is usually when you want to see things like being like very interactive. When you want to do things at scale, things should be more programmable. So all the functionalities that I'm talking about are exposed as a Python SDK. So this does exactly the same thing, but just in a Python script. So you just like instantiate a client, and then client.create branch, client.import data, client.run, client.merge. Why I'm insisting a lot about so much on the APIs. The migration was essentially possible in a very smooth way because of two main factors. This is the first lesson that we really learned by working with these guys. One is a built-in feature of Iceberg. So we don't really have to move the data outside of S3. That really facilitates the starting point. Like we can kickstart our migration without thinking too much. But if you have very, very simple APIs, you break this down in different phases, and we're actually able to migrate most of your tables in less than a month, which, considering, you know, like talks that I've seen here, and I know that most of you guys like know how complex things are in large enterprises, is kind of a miracle, which is the reason why this talk is called Miracle on Iceberg. And the reason why it's so easy is just like, you have like the first POC that you can do literally with the snippet of code that I showed you, where you, just like with the CLI, you do like, okay, let me try to migrate like a couple of tables just to see whether this is the kind of stuff that we want to do. And the developers could do that like in just like a couple of, like in a few days, right? Once you establish that this is doable and the APIs are very easy to learn, and now you can script it. And so the bulk of the migration is going to happen once with a bunch of scripts. Now, this is a more complex thing to do, but because the APIs are simple, not that hard. And then finally, because now, you know, like if we have like a portion of our data now migrated onto Iceberg tables, and this is a large company, so, you know, data keep coming in, they have millions and millions of users every day, we want to put this in an orchestration workflow. It's just a Python SDK. So you take literally those scripts, you break them down into tasks. Mediaset chose temporal as their orchestrator. And basically what you're going to end up at the end is just a bunch of tasks that are going to call methods that are exposed via the Python SDK, and that's all. So really, like the first lesson that we learned in helping them with this migration is that Iceberg plus good APIs make migration extremely easy and makes it progressive. We don't have to buy into the concept that for the next year and a half, we will have to do the migration. We can do it like bit by bit. You end up having like a very simplified architecture if you buy into this design. So you essentially have your data in S3, Iceberg. Most of your compute is going to be just like serverless functions. So you can think of this like if you were like running everything on Lambdas or something like that. It's that simple, right? And then, you know, like then for the more interactive use cases, you can either use the compute that is already provided with a platform for like the smaller things with DuckDB. If you need like more juice, you can use Amazon Athena, or you can pour things into a different engine, because ultimately this is now an open stack where you like all the states of the system are maintained as Iceberg tables, right? But most importantly, now we can support both SQL and Python, and we get rid of Spark, which is like a big deal. Of course, like because like Iceberg is open, and now potentially I can start like, you know, adding engines and support like even more use cases, like become more intentional in choosing the different runtimes and the different engines depending on what people need to do. So lesson number 2 that we learned is simplicity really, really, really helps with developer adoptions. And I attended a few talks today, and I see that this is like a general concern, like it's really hard to bring something new and have people, you know, adopt it in a large company. But in a few weeks, we went from like the 2 renegade engineers trying to do that with, you know, like tens of thousands of branches that are created on the platform every week, and runs and imports run every week, and more than 6,000 interactive queries. And the only reason why this is possible, it's because it's simple. And basically none of the developers, so the Spark people were just like, oh, okay, this is different. I kind of like Spark. It was like, okay, good for you. But everybody else was just like, oh, I understand this. I don't have to go through Spark, or I don't have to go through the data platform team to ask for that. And so that's how you get like a viral adoption in the organization. Is just, you know Python? Yes. You have access to the S3 bucket? Yes. You're good to go. This is one of the case studies that we did with them. And I like this because it's a fairly complicated use case that was somehow impossible before, and now it was all of a sudden possible. And a lot of that is really, so it's complicated for 2 reasons, right? It's complicated because of the data science problem that we're facing, and it's also complicated for the infrastructure, but ideally you would like to focus on the first, and the second part should not get in the way. So Media for Europe is also an advertiser. So it's very important for them that they have a good understanding of what they can do with the ads that they can sell. And they have a way to sell ads and a way to deliver ads to the final users because they have so many media touch points. This is what it looks like. You know, you have a TV show, you have your slots there that you can, where you can serve an ad, okay? So you're gonna end up having like data from various sources here, very different types of data. You have the data about the user, because the user is a registered user and we know who he is and so on. We're gonna have data about the video, so how is this video performing, how long, like what, you know, like what TV show is that popular or not, and so on. You're gonna have now data about the timeline specifically viewed by this specific user. So for instance, if the user at a certain point leaves the web, like the streaming, that is an event that you have like in the timeline data. And then you have the data about the ads, how much it costs, you know, what is our marginality on it, like is that an efficient ad to run and so on. What we want to know in this scenario is, what if? What if, as slot number 2, we run 2 ads instead of 1? Does that make it better, worse? Like, does the user leave or does the user stick around? If the user sticks around, I can actually sell 1 more ad. There's a lot of parameters you can play with this, like how many ads, like how many slots, how long is the ad. So there's a number of what-if scenarios that you want to consider. But if you want to do a what-if, this is a counterfactual question. So you basically have to train models on sessions that are similar to the one that you want to target, and then use those models to make predictions. So you have to create like digital twins. And in a scenario like the one that I showed you, where there's so many different data sources, doing this on a data platform is not easy, because you do have to take care of a bunch of stuff. You do have to take care of the data layer, so you need like a platform that is easy for you to pull all the data from different sources, put them in one place, and then, you know, like easily create like a schema that you can reason about, right? You also need point-in-time data sets across tables, because you're actually effectively trying to do possible worlds computation. Like you're trying to see what happens in counterfactual situations. So it's important for you to be able to travel back and forth in time. You need SQL because you have to join a hell lot of data from different data sets, different, you know, schemas, different everything. And you need a lot of Python, because the data science problem ultimately is hard here to solve, and it requires, you know, PyTorch and Jensen and scikit-learn. So it's not a trivial data science problem. So ideally, you want a platform that takes care of as much as this possible, so you can focus on the last piece, because the last piece is hard. So in the design that I presented you, this is kind of like possible, because now we have the lakehouse design that beautifully takes care of the variety of data sources and the single source of truth. Basically, everything is an iceberg table. Great. And everything is in S3. And now I can run my compute using Python or SQL and use the branches that I showed you to do the counterfactuals. So branch number 1 is a what if. Branch number 2 is a what if. So the complexity of that use case kind of like disappears into just like running Python functions on branches, which feels like a lot like just coding. So the lesson that we learned also is that Python should really be a first-class citizen for the lakehouse, because like most of the really high value business use cases that we saw with this customer are actually data science, ML, and AI. And the language of that is Python. So I'm here basically to advocate for a Python lakehouse, mostly because like I really believe that Iceberg has very good ergonomics for data science. And I think that this is overlooked right now. Schema evolution and data versioning are really, really great for the iteration that data scientists constantly need to do on data sets. It's just that if you just throw Iceberg at a data scientist, they wouldn't know what to do with it. is just not the kind of tool that they're used to. So there's a lot of like, we need to put some work in exposing those capabilities in abstractions that resonate to that population. And Python is just the lingua franca for it. So I think like this is part of the kind of like broader design of the lakehouse and the vision. If you go back, you know, to the original paper from the Databricks folks, a lot of that is about this, right? It's about just like, oh, it's great. You can do a lot of use cases. We can do finally both analytics and AI and ML on the same one. But if I have to be like really, really honest, I think that right now, Python is a little bit of a second-class citizen in the lakehouse. And because like most of those use cases are taken care of by Spark. And what you hear is just people saying like, you can totally do that. You just do a Spark notebook. But there's a gigantic population of data scientists and machine learning people who just wouldn't do that if they just had Python. They would be faster. It would be easier for them to learn it. They would be just like happier developers in just running things in Python. Iceberg is a really good start, and I'm really, really happy to see that in the past year has been a lot of work has been done in kind of like bringing Iceberg up to speed. But I think that the mental model, how many of you guys like use PySpark? Iceberg? Okay. I think like the mental model, at least like that's what I gather, is a lot like, I'm going to have like a Python process on my laptop, and I'm going to use Iceberg to, you know, connect to a catalog that is in the cloud, and I'm going to run things and I'm going to do pandas, okay? Which is okay, I guess, but like, first of all, things at scale are not done like that. Secondly, you know, you pay egress fees, you have a lot of security concerns in enterprises because you don't want people to download data on their laptop, ideally. It's not really performant because you're basically going over the wire, so the bandwidth is gonna become like a gigantic bottleneck. The same goes for, you know, just scaling your compute, because ultimately you're doing this on your laptop. The environments will kill you, because like Python environments are really hard to, you know, maintain at scale, and now we have like all people doing different things on different machines. So like, really, the Python lakehouse should devote some attention on building vertically integrated Python runtimes. And that's my final kind of like message for you guys. What that means is that, wouldn't it be nice if we have like a Python runtime that is explicitly built to run data pipelines at scale in the cloud and is as vertically integrated as possible with your lakehouse? Because in one design choice, you can wipe out a bunch of the limitations that you have today. You do no longer have the egress fees. You no longer have the security issues because we all work in the same cloud. We can manage our, you know, functions, like our dependencies and environments better because we have containers. The cloud bandwidth is 100 times faster than going over the internet, so it becomes like really, really easy for you to query data in and out. You don't have problems in scaling because now you're running with the cloud, so you can multi-thread, you can vertically scale, potentially you can do distributed. And I think like the more subtle point there is, if your Python runtime knows about your data, you can do optimization. It will never be like a query optimizer. I get it. It will never be like a database. But there's a lot of stuff that you can do if you know the shape of the data. I showed you a function that has a table as an input. If I know what that table looks like, I can avoid doing stupid stuff like reading the same bytes over and over. I know what the table looks like from that Python process. So I can do differential scan. I can do caching. I can do caching at the scan level. I can do caching at the DAG level. So I know that certain artifacts didn't change. So if I'm running a 90 node pipeline and something changes at node 50, there's absolutely no reason to run it from the beginning. So I can just like run the children, right? So there's a lot of optimization that we can gain in the runtime if we start thinking in this perspective and build more verticalized solutions for Python. So recap of our lesson learned. Iceberg is absolutely awesome. It would have been absolutely impossible to think about a migration with a different paradigm. Good APIs make a lot of difference when it comes to both make sure that people are able to adopt innovations that you bring inside of your organizations, and they make migrations remarkably easier than it usually is. And we truly believe that Python support is needed for AI ML. There's a lot of use cases that are natively done on data lakes for historical reasons, and now are kind of like aside of the typical use cases of the lakehouse. And we hope that that changes soon. And that's why we're building essentially a Python lakehouse. If you want to talk to me, I'm here. I'm going to hear the whole week or something like that. Thank you very much. Questions? Yes.
How long it will take to make PyIceberg distributed? Like, how many versions do you take?
PyIceberg right now, like, we don't run PyIceberg as a distributed system. Like, we essentially, so what happens here is this basically goes into, so the iceberg table like becomes an arrow table that gets streamed inside of our fast runtime, and then it remains an arrow table basically across the pipeline up until you write it back into Iceberg. It's not a distributed system right now. What you see here is just a big box of compute for at the current stage. We tend to focus more on reasonable scale workloads. They're not gigantic. I think for the gigantic workloads, it's actually like it's good for you to use Spark. I think like the argument or broader argument that we're making is there's a lot of Spark jobs that data scientists especially use that are not necessarily needed for scale reasons.
So there are a bunch of workloads for WDB with Iceberg is going on. You think WDB?
Yeah, like the platform that we built with these guys is basically to, you can run Python or you can run SQL. When you run SQL, you run DuckDB. So yeah. Yes?
I might have missed this in your original description of the case study, but how much iceberg did the customer already have, like, before you guys showed up? Zero.
Zero. It was just Hive tables. Yeah.
Interesting. And so was there any effort, like, did you have to sell them on iceberg at all as well?
I think that so in this specific case, I think like Iceberg ultimately becomes almost an implementation of detail, right? What it really matters is how many people in a company can use this thing. That was really the selling point. Iceberg is, the design choice that we made in integrating like a certain vertical tabular format in the platform. I think they were already looking at Iceberg as a possibility for them to simplify their stack. I don't think that it was immediately clear to them how to go from, hey, Iceberg looks better than Hive, to, hey, this is how we're gonna expose those functionalities to all the data scientists in the company. So I think like that was like the major gap.
Yeah, makes sense. Interesting.
Yes.
So if you change your schema, right, and then you do another migration, the data files are going to change, or just the metadata, or that's delegated to the Iceberg maintain?
Yeah, that's the point. Like if you migrate, you mostly like add metadata files, right? Mm-hmm. That's the beauty of migrating into Iceberg, is that you don't really have to copy your data around. Mm-hmm. So one thing that I think like helped in this case, like I've seen like other talks today where people are really using Hive tables, and so now we have to swap these tables with other Iceberg tables, and it becomes like really hard for people to learn the new thing or just like trust the new system. One thing that definitely helped us is that this company particularly had Hive tables, mm-hmm. and just a handful of people that could really operate that system, mm-hmm. and they wanted to open it up to people who never had access to the data. So when we came along, it's just like, hey, there's a bunch of tables for you to use. We didn't really have to convince somebody who built its own expertise or entire systems on Hive to migrate. But it was more just like, oh, thank you. Finally, I can access the data without having to go through, the people that really understand Hive.
But then if some team, for example, they want another partition for example.
Yeah.
Because the use case, right?
Yeah, That's what I'm saying. Like not many, like most of the teams that kind of like got access to the new tables didn't have a lot of preconception of how tables should be partitioned. They basically wrote their partitions directly in Iceberg.
And in your experience, for example, if let's say that you want to expose the Python function, right, to a customer, not to the team. Let's say, for example, you have
Okay.
30 queries per minute, right, for customers, right? How performant is that? I mean, this is just a question. I mean, let's say that you are running those queries, but for customer, not for, as I saw in your example, you have that.
Wait. So are you talking? So you're talking about like interactive queries, or are you talking?
Yeah,
You're talking synchronous or asynchronous?
No, synchronous, but I mean.
Synchronous. Okay.
But
So synchronous is going to be probably
knowing
SQL.
your data, right? Not just random queries around, right? Let's say I want to know the last 30 days of,
Fantastic.
whatever,
Yes.
right? Yeah.
So, but like in that case, then it becomes like so. That use case looks a lot just like querying Iceberg tables.
Yeah.
So it depends, like the performance, like that. It depends on a number of choices you want to make on your use case. So you can use like, Trino. You can use, you can use DuckDB. You can use something that is hosted like Athena. So it depends on what you want to do with that.
Yeah.
But like the asynchronous case, I think is less compelling for Python, just because you don't necessarily use that a lot. Like Python is, at least like how people use it in our platform, is more for like batch and asynchronous jobs. Like you don't run a query.
Yeah.
It seems like most people are okay with just like running a query in SQL rather than just like, you could in theory, but it's kind of more complicated, it's more convoluted than it should be.
I agree, yeah. And the last question, sir,
Go ahead.
is that how do you distinguish between using DuckDB
Yeah.
and other stuff? I mean, it's just because I've seen in these talks like, oh, we are going to use DuckDB, right?
Okay.
And then for other use cases, we're going to use,
My experience with DuckDB is that DuckDB is like has a number of advantages. It's very performant. It's completely in memory. So you basically have like one process, and you basically just got like your database in memory. And it's very, very simple. It's also like your Python extensions, like your languages together are pretty simple to use. Really not good if you have to do like very large queries, because you kind of have to provision like an insane amount of compute up front. Like it's going to go out of memory. So there's a number of reasons why you don't want to do that. But my experience is that also, even in very, very large enterprises, most queries are not super large. You have like gigantic queries here and there, especially, if you think of a DAG in the beginning. But like in my previous company, I think like almost 40% of my Snowflake bill were just random queries. Were just like people going like, oh, how many things happened last week? So very simple queries. So there's a lot of, your workloads then also tend to kind of like break down into smaller workloads quickly. So you might have like a gigantic job in the beginning, in the asynchronous use case, I mean. They become like smaller. So I think there's a lot of room where you can use stuff like DuckDB in your everyday life, actually. I think it's very useful technology. Last mile query, exactly. Last mile queries are just like usually very punctual, so it's not, yeah. But look, like even even mid-mile queries, like even.
So is there a recommended typical dataset size that works better for these kind of, because it's mostly a one node process?
This is a one node application now, so I think like what we like our sweet spot is anything that is like too big for you to be okay with doing stuff like on your computer, and smaller than a terabyte. So anything is like in that range, this is blazing fast and very easy to use. If your queries start to become like 1-2 terabytes, they're just, yeah, because the AWS just doesn't have enough big machine. But again, like, I might be wrong, but like one, I think, lesson that at least I kind of learned is when the big data movement came along, the story was, well, we're going to need big data technologies because the data is going to grow exponentially, and we're all going to draw in data. And that sort of happened. What it really happened, though, is that the largest machine that we could have when Spark came out for the first time now is smaller than a Lambda. So to a certain extent, like the ability of our species to just build bigger machines in more affordable machines in the cloud seems to be better than our ability to just like produce a lot of data we're going to use.
It's more of a scale up rather than scale out in that sense, right?
Yeah.
Going back like 15 years back.
I think like Spark, like there was a moment in history where like, of course you need Spark, because like how else you can otherwise like compute like a data set? There are no machines that can do that. Like I have to split up. Right now I think is a contentious case. Like it depends on what you do. Like some of them yes, and some of them you can just like fit them in one node.
And when you're talking about like 1 terabyte or less than that, for mostly analytical workloads here we're talking still, right?
We do also training. Like we do also training. Yeah. So, but yeah.
But this isn't like, I'm trying to understand what is the real world use case that kind of fits this smaller data set.
All the data transformations for all the data science use cases and the machine learning use cases are way below 500 gigabytes in a company that processes like data from video streamings from 24 million people.
Okay, but data lakes are big because okay,
The data lake is gigantic. The data lake is insane. The data lake is 80 petabytes. Yeah, but like,
this application is touching only
absolutely, absolutely. Yes, the data lake is insanely large. Yeah, you're right. But like, how much of that data are you going to use on Monday? You know, certainly not all the 80 petabytes. That's the point. Thank you. Yes.
So I think that your current strategy is to be Python native, right? For example, you support to, for example, add some decorators to use pandas or to use QS Spark to run those things on your cloud. So how could you deal with customers who already run the services on EMR and to run the Java stack? Because in here the migration cost is not trivial.
Yeah, that's a very good question. So there's a utility in the platform that allows us to run your Spark code if you want. So some of the migration, I didn't show it in this talk, but like some of the migration is just like sandwiching Spark jobs in those decorators. So you have the same interface, but you can run the Spark behind the hood. I think that the specific people that we serve and the use cases that we go after is actually teams that are not super comfortable in having everything on a JVM-based system. That's like, it's a feature, not a bug. In our case, the fact that we don't rely on the JVM. Because like a lot of the folks that use our platform are effectively people that that are good at Python, but the JVM kind of like spooks them. Yeah.
So have you tried using rapids? I heard like the rapids can seamlessly accelerate the
Yeah,
Python workloads.
that's a very good question. Yes, like we worked with the folks at NVIDIA in the very first version. Like we don't, like the truth is that right now we don't have a very strong use case for rapids, but it's an interesting area for us to expand. Like right now we don't really need it.
Got it.
Yeah.
Because the processing itself is smaller here.
But yes, you're absolutely right. Yes.
Got it.
Yeah. Yeah.
It's too big a hammer for the nail.
Yeah, exactly. Like right now it's still like that, but like I would assume like in the next months that's going to be like more like that.
Thank you. And you have plans to kind of go take it distributed for some reason?
At a certain point, I think we have to bite the bullet.
That's the things will come into play.
Yeah, pretty much, like yeah. Like we can procrastinate as much as we can, but like at a certain point, yeah.
Looks like enough to, I think, lunch here.
Absolutely, yeah.
Thank you.
Thank you. I think we're done, guys. Thank you for coming.